Hello and welcome. In this exercise, we are going to solve a single flow passing through an open steady system using a suitable test step. The system is open, system is steady, and there is a single flow, one inlet and one exit. We'll do mass, energy, and entropy analysis of this problem. We'll begin with the problem statement, a very standard problem in open steady systems. Is an adiabatic turbine. That means there is no heat transfer. The turbine is adiabatic, and it's operating at steady state with a mass flow rate given, inlet conditions given, exit conditions given, and we are asked to find the shaft power and the entropy generation and isentropic efficiency. So just to put this in perspective, let's quickly draw the system on a TS diagram to see what is going on, what are the different states we have to compute. So obviously we have to use the PC model. There is a possibility of phase change, and so I draw the dome, and let's say the turbine, the high pressure line, 6 ampere line is here, and the low pressure line is, let's say, somewhere here. So what is given is that at the exit, quality is 100%, so obviously exit state is somewhere here, and let's say inlet state is somewhere there. I'm just assuming instead of calling it state 2, I'm calling it state 3 for a particular reason, because I want to call the isentropic state state 2. This is just a convention. That's why I'm naming them like that. So state 1 is our inlet state, everything is given. State 3 is our exit state, everything is given. And state 2 is our isentropic state, same place, except the assumption is that there is no entropy generation between state 1 and 2. So that will be our ideal turbine, 1 to 2, and 1 to 3 is our actual turbine. Okay, with this setup, let's begin. We're going to enter the known conditions for the inlet state 1 and 3, and we'll create an isentropic state using constant entropy. So let's launch the test calc first. I've already logged in to the thermofluids website, test calcs, and again it says system analysis. We follow the open branch, open steady, generic, single flow systems. There's only one flow passing through the turbine, and we launch the PC model right here. Let's evaluate states. Mass flow rate is given. State 1 is 5 inlet state, 5 kg per second. Pressure is given in million pascals, 6 MPa, and temperature is given 500 degrees Celsius. The state has been computed. Basically, enthalpy has been found. Let's move to state 3, which is the mass flow rate must be the same. Mass flow rate is the same. Pressure is given as 4.5 kPa, and the quality is given, which is here. Quality is given as 100% or 1 in fraction. So it's a saturated vapor at the exit. A calculate brings it up. If I go to the graphics panel, we can verify that state 1 is somewhere there. State 3 is saturated just as we expect. So in the IO panel, we can find out the actual work. Suppose we call it W dot actual. M dot 1 J3 minus J1. We could use H instead of J, but it's always a better practice to use J, because in case you want to include kinetic and potential energy, you will have it should be J1 minus J3, because of course J1 is higher than J3. We want the answer in positive number. W dot A actual produced by the turbine. The inlet energy is higher than exit energy. So the answer is 4320 kilowatt. So this is how much power, shaft power, the turbine is producing. How about it's an adiabatic turbine. we can calculate the entropy generation as dot gen by simply using the second law. And as we know, if we go look at that, the second law is telling us that there is no heat transfer, Q dot equals 0. So S dot gen is simply m dot SE minus SI, that is the exit minus inlet. So if we come back here, the formula becomes entropy generation is m dot 1 star. The entropy that is exiting will be higher, S3, minus what is entering. So the difference is what must be generated by friction, 7.76. So this is our answer for entropy generation rate in this turbine. And what is the last part? We are supposed to also find the isentropic efficiency. So to do so, we're going to find out the work output from an ideal reversible turbine. For that, let's go and evaluate state 2, which will have the same pressure as the actual turbine at the exit. However, it will work isentropically, and that's the definition of a reversible turbine. There is no heat transfer, there is no friction that leads to the condition that the turbine is isentropic. Of course, the mass flow rate also remains the same, m dot 1. So what is an isentropic exit state? It is at the same pressure as the actual turbine's exit state, but we assume that there is no friction in the turbine and there is no heat transfer in the turbine. So therefore, a second law analysis, look at the entropy equation. If there is no heat transfer and no entropy generation, the two entropies at the inlet and exit must be equal. And that's called the condition for an isentropic turbine. Once we found the isentropic exit state, we can find the ideal work, W dot ideal m dot 1 star J2 minus J1. And oh, sorry, again I made the same mistake, J1 minus J2. J1 being higher, J1 is what is coming in, what is going out, the flow energy will be less because energy is extracted by the blade, by the shaft. So look, the ideal work is way higher than the actual work. So what is the isentropic efficiency? Efficiency equal turbine efficiency, or just efficiency, W dot actual divided by W dot ideal. I hope I got my spelling right. Yes. And that turns out to be 0.646 or 64%. Let's go one step beyond and see. So what is an isentropic efficiency? That means if everything being the same, just friction was eliminated from the turbine, and we are still developing, you're still delivering steam at the same pressure at the exit, but the temperature could be different. Notice that at state 2 and state 3, the quality, the state can be very different. If you go to the graphics panel, look, this is the isentropic exit. Only condition is the pressure is the same as 3, but temperature or quality or the state is not the same as 3. So even though it's an ideal turbine, the exit condition is different for this ideal turbine. But there is another kind of ideal turbine. Suppose we say, you know what, state 1 and 3 is actual inlet and exit, and we don't want to mess with that. Can we make the turbine any better? Yes, and that's called a totally reversible turbine for the given inlet and exit conditions. Such an efficiency is called exergetic efficiency. To find such exergetic efficiency, all you have to do is to go back, find the dead state. Suppose the outside ambient pressure is 100 kPa, ambient temperature is, you have to know the ambient condition. Once you know state 0, the dead state, notice that all this, the psi is the flow exergy is calculated. Just like J, the flow energy tells you how much energy is coming in, psi tells you how much useful energy is coming in. There's always energy, but you may not be able to extract that easily, but psi is something that tells you exactly how much energy you can extract. So now that we know how much energy can be extracted from the turbine in an ideal situation, we can find out Suppose we write down exergy difference, for lack of a better term, m dot 1 star, see psi 1 is coming and psi 3 is what is going out. So what is that quantity 6635 that we just calculated? That says that the useful energy that comes in minus that goes out, the difference is this. In other words, the turbine could have produced 6635 if it were a reversible, an ideal turbine, an engineer's dream. So that turbine, notice, is not changing the inlet or exit condition. We are replacing the turbine with this reversible turbine, and it's producing more work. And that is the exergy difference that is producing. So currently it is producing how much? W dot actual. So this difference is known as exergy efficiency or exergetic efficiency or second law efficiency. Exergy efficiency would be how much? The actual is producing W dot actual divided by which is 65.1%. So notice that these two efficiencies are totally different things, even though they're close to each other. This is isentropic efficiency, and this is exergetic efficiency. This is covered in chapter 6 of the book, and this is covered in chapter 4 of the book.